So Klaus Ensslin, I believe it's a very known name. He studied physics at the University of Munich and at the ETH Zürich, and he completed his doctoral dissertation at the Max Planck Institute in Stuttgart. And he also worked as a postdoc at the University of California in Santa Barbara, USA. He then worked on University of Munich, and his primary research interest lies in the physics of mesoscopic systems, the electronic properties of novel semiconductor nanostructures, which he investigates using material control down to the atomic nanoscale. So one important goal is the ever-increasing control and improved understanding of the quantum properties of electrons in nanostructures. This course will be about technology and physics of semiconductor quantum bits. And please, Klaus, the room is yours.
Thank you very much, Božena. Thank you for having me here. Thank you, everybody, for listening. It's too bad that I can't be with you guys in Brno. I always like to be there a lot. Lots of friendly people, competent sciences. That is fun. So now, this whole thing, as you know, is a bit anonymous. I mean, right now, I just see myself. I don't see anybody else. I have a few questions during the talk, but I encourage you very much to raise your hand or tell Božena that you have to ask a question. That is super welcome. I think it makes it more entertaining for you and for me. I plan to have a short break about halfway so that you can relax a little bit and then we can continue. So I will talk about the technology and the physics of semiconductor qubits. This is a wide open topic, and I will give a very general introduction to tell you a little bit what the main questions are, and then be a little bit more specific the further we go on what, for example, is also going on in our lab. So I just get a request, an annotation request. Okay, I guess I approve it. I don't know what it means, but aha. So somebody wants to annotate my transparencies. That sounds interesting. Let's find out.
Sorry very much. I just click on unknown icon.
Ah, okay. Doesn't matter. Now I have to get rid of my okay. So here is my first question. Božena, would you be so kind and start the poll? So just that I get an idea who is attending. Are you a PhD student? Are you a postdoc? Or are you something else? So I don't see anything. Božena, is the poll open?
I believe I will have to stop sharing the screen for a moment, yes?
Maybe okay, good. I still don't see anything. Is the poll up?
I can't. It doesn't seem to work for me.
Okay, maybe I have to do it.
No, I can do it. Just to. It should work now. Yes, the poll should be now opened.
Okay. Yeah. So, Božena, can you let the others see the result?
If everyone's finished, I believe.
Mm-hmm.
Yes. So I don't exactly know how, but we have 25% of PhD students, 17% of postdocs, and 23% of others.
Okay.
And 35 who didn't answer.
Okay, that's all fine. Thank you. Okay, now I need to share my
Yes,
screen
I
again.
will. I will give you the ball. Just need to find it.
You see it again?
Yes.
Okay, thank you. Okay, let's start with quantum computing. What is it about? And don't worry, I don't go into many details here. On the right-hand side, on the top, you see what is called a Bloch sphere. And the Bloch sphere basically is a phase space that characterizes a quantum mechanical state. So we all know that you can have a 0 and a 1 state in classical computing that is called a bit. And if you then write a quantum mechanical wave function, you know that you can write it as a superposition of a 0 and a 1 state with the coefficients C0 and C1. That could be anything. And depending on these coefficients, C0 and C1, that will determine the location of your quantum state on this Bloch sphere. Now, one of the simplest thing is a spin 1/2. And you know that a spin 1/2 is like a magnetic moment, and that magnetic moment could look upwards, downwards, or it could be, have an orientation in the plane. It could have any orientation as indicated on this Bloch sphere. So a spin 1/2 is always a good representation of a qubit. Now, if you have many qubits, then you can write them in this superposition coefficient. And the very important thing is that the number of coefficients goes with 2 to the n power. So that's where all the information is in. It grows exponentially with the number n. And actually tomorrow, if you're still willing to listen to me, I will show you a very nice example where you see this n being effective in a very straightforward setting. Okay, so there are, as you know, no quantum computers yet that do work that we couldn't do on a classical computer. The expectation is that there's exponential speed up for problems that are of parallel nature. One of them is factorization of integers. We do have an algorithm for that implemented by Shor, but it doesn't work yet. We don't yet have the hardware to do this in an efficient way. But the software is there, the ideas are there, and the hardware is what we're going to discuss. So the idea is to do fundamental logic operations, which means moving around on the Bloch sphere for a single qubit, or if you have many qubits, then it will be a more complex state that needs to be understood and manipulated. So you see now on the Bloch sphere on the top right corner, you see this arrow moving around in the plane. And that basically means that we have now these different states in our system. Again, a superposition of S and A, the top and the bottom part. So in this particular case, it means that you have a vector that rotates in the plane. Now, if we calculate what happens as a function of time, we have this Hamiltonian here. The delta is the relevant energy scale. And then the Hamiltonian is simply given by what you see here in the last line here. It's the S state plus a number times the A state. And you can clearly see if the delta T is equal to 0, we recover the state on the top. And otherwise, it just means that the vector goes around, as you see in the schematic on the top. So these are nice pictures, simple theory arguments that have been put forward, of course, years and years ago. Now, how does the hardware look like? And I stole a transparency here from the internet. I don't even know where I stole it from, and I manipulated it a little bit. So here is a zoo of qubits, right? You can take neutral atoms and atomic lattices. There is atomic cavity QED trapped ions is a very strong contender. Solution NMR comes from chemistry, was actually the first ever quantum computer built now 15 years ago, but it has its limits. That's why this is no longer pursued. Then there are all the superconductors that can be used in different versions to make qubits. semiconductors, you could do optical experiment, electronic experiments. There are ideas using spins in semiconductors, and there are very exotic ideas all around. So I think everybody these days who has a quantum mechanical two-level system just calls it a qubit, and then it becomes a modern piece of science. The question is, what are the good qubits? And I will talk a little bit about that. So I think the best today are the trapped ions and the superconducting qubits. I will talk about spins and charges in semiconductors. They are not as advanced yet, but they have the potential to benefit from all the semiconductor technology that we have around us for classical computing. And you see this green dashed line here? I think this green dashed line basically separates very different hardware worlds. So on top of this green line, you see everything that is tuned with lasers, vacuum, manipulation is done mostly optically and so forth. And on the bottom right-hand corner, you see everything that is done in the solid state. So it's something that needs a clean room where you have electrodes and magnetic fields and stuff like that. But it seems that the two worlds are actually converging, and more is done in a similar fashion. So these are examples of qubits, how they are pursued in many labs around the world. So I will focus on basically two kinds of qubits that are electronic states in quantum dots and spin states in quantum dots. So charge and spin. Now let's start in a very basic fashion. Quantum dots are islands in three-dimensional space where charge carriers are confined in all three dimensions. They are also called artificial atoms. In real atoms, as we know, the confinement potential is a Coulomb potential. It's 1 over r-like. And you can think of a quantum dot, it's just like an atom, but the confinement potential is not a Coulomb potential, but it could be a harmonic potential or some other confining potential. So in a very simple approximation, you have a particle in a box. We know how to solve the Schrödinger equation. These are the energy levels. And we can put in typical numbers here. So the L maybe is of the order of 10 to 100 nanometers or so. So the spacings here are of the order of 0.1 milli-electron volt. So that's something like 1 Kelvin in temperature. And you could use the very same argument if you put in an L here for the size of an atom, make it half an angstrom. The same equation gives you energy scales of the order of 10 electron volts. So you see we are roughly 4 or 5 orders of magnitude different in energy scale compared to real atoms, but the physics is very much related. Okay, now these electrons, once they are on the quantum dot, they repel each other. There's Coulomb repulsion. And you know that if you can consider such a spherical object in 2 dimensions, it would be a circle, but in 3 dimensions, it's a spherical object like an atom. And you can calculate the capacitance of this object, and you can calculate the corresponding charging energy, as it is called. The charging energy is the energy it takes to add a charge to a capacitor. And this energy scales with Q squared over 2C. So it's a classical expression, no quantum mechanics here. And it simply tells you that there are charges on your capacitor. And if you want to add another charge, it costs you a certain energy. And that energy scales with 1 over C. So if you have a large capacitance, this energy scale is very small. And so if you go to the extreme limit, that you take 1 electronic charge and you take a typical capacitor, this energy scale is negligible for all practical purposes. So if you go to the machine shop and you get yourself a capacitor that is 1 nanofarad, forget about this charging energy because it's way smaller than kT. If, however, you make this C very small, then this energy scale gets large and becomes actually larger than the energy scale that I discussed before, the energy scale that comes from the quantum mechanical confinement. So if you just plug in a few numbers here, let's say this R is again of the order of 10 to 100 nanometers, then you can calculate the capacitance of a sphere. You plug it into the equation for the energy, and you see that this is around the millivolt. The previous energy scale was about 1/10 of a millivolt. So these classical charging energies related to capacitive effects are 10 times more important typically than the quantum mechanical confinement energy scales. For atoms, it turns out it's about the same energy scale. It's actually a very interesting question in atomic physics, how you can model a quantum mechanical object like an atom simply by using this classical capacitor model. And you can find amazingly many answers that are not completely off just by using these classical arguments. Okay, now let's assume you have such a quantum dot, and I will explain in a moment how you do it. Then it is embedded in something. It's embedded in a solid. And that's the beauty of a quantum dot. You see, if you have a free atom, if you want to handle a free atom, you have to position it somewhere in free space, in vacuum, and you have to trap it with lasers and all kinds of tools that are available, but they are complicated experimentally. Once you have a quantum dot fabricated in a solid state system, it's something you can touch with your hand. It's something that you can walk around, and it's something that doesn't change. It just stays there. A quantum dot is a quantum dot. Now, this quantum dot lives in a solid state matrix, and this solid state matrix has lots of degrees of freedom. It has fluctuations of electric and magnetic field. There are spin orbit corrections. There are nuclear spins that could couple to the electron spins. There are possible optical excitations like plasmons. You have electrodes connected, gate electrodes, source and drain contacts that are connected to your outside power supplies that have a finite noise. You have phonons in your system because you're at finite temperature. You have photons that even come from, for example, because you're at finite temperature, you have black body radiation, and all of this couples to your quantum dot. So the advantage of the quantum dot is that basically you take a tweezer and you take it with your hand wherever you want. Comes with a disadvantage that you have a lot of degrees of freedoms that couple into your system and give rise, for example, to decoherence and dissipation. So from an engineering point of view, I would say that's a nuisance. We would like to get rid of it. From a physics point of view, I would say all of that is interesting because these are degrees of freedom that make our system complex, and complex systems are not so easy to understand, so that makes them interesting. Now, let me show you an example of a quantum dot. This is a top view taken with an SEM of a piece of gallium arsenide. This gallium arsenide heterostructure is grown by our colleagues. This is done by Werner Wegscheider here at ETH Zürich. And they basically contain a sheet of electrons, of highly mobile electrons, just below the surface. And you see here that on top of this surface, we have this pattern of metal gate electrodes, and we can apply voltages to each of those electrons. And it so happens that if we apply a negative voltage, we deplete the electrons below. So it's like a standard transistor. You have a gate electrode, and you can tune the charge carrier density below the gate electrode by applying a voltage to the gate electrode. It's like a capacitor where one plate is metallic and the other plate is a semiconductor electron gas whose density can be tuned or even switched off. So now let's assume we apply gate voltages to all of these 6 gate electrodes, no carriers left below them. So what remains is this little island here in the center, which we call the dot. And you see it's coupled to the outside world through these little gaps that can be electrostatically tuned. And out there we have macroscopic source and drain contacts where we attach our bond wires and our multimeters and whatnot. So this is a little island. It's small. It's much less than a micron in size, maybe 100 nanometers or so. And it contains charges. It may contain only 1 electron or only 2. And electrons from the source to the drain contact, they have to go through this quantum dot. And now we have this phenomenon of strong Coulomb interaction. So let's assume there's an electron on this dot. Another one wants to come from the source electrode. Well, it's repelled by this electron already on the dot. So you have to provide enough energy to overcome this repulsion if you provide that by simply applying a bias to your system. So you provide the energy by applying a voltage bias to your source contact. Then the electron goes onto the dot and then off to the drain. And this is by construction, one electron after another, because if one additional electron is on the dot, then the next one can't come because, again, of Coulomb repulsion. So it's a very tunable system, and it has been around for a long time. So here is the phenomenon of Coulomb blockade schematically. So what you see here is the source and the drain. They are standard metals, so they have a Fermi level. The temperatures are usually very low. We measure typically at 10 millikelvin to 100 millikelvin. That corresponds to energies between 1 and 10 microelectron volts. So you have electrons here, electrons there. In the middle, you have this quantum dot with confined states. And the electrons from the left to the right, you see there's a potential gradient because of the applied voltage bias. In this particular case, there is no state that they can go through. So the lower state is filled because there are occupied states left and right. So this state is filled. This state is empty. So at the two Fermi levels, there's nothing. And therefore, no current can flow. This is what we call Coulomb blockade. Now you can raise these states up and down by applying a gate voltage. And you can raise one of them to be between the Fermi levels or between the chemical potentials of the metals left and right. And now you see that one electron after the other can go through. That's resonant transport. And the experiment looks like shown here on the bottom graph. You see the current on the vertical direction. That's, you apply voltage here, you measure the current. You see the current is small, picoamps. On the horizontal axis is this gate voltage that tunes the ladder of states up and down or controls the number of electrons in your system. And you see the current is zero most of the time. This is this configuration of Coulomb blockade. But every now and then there's a sharp conductance resonance. And this corresponds to the situation that one of those states is put resonantly between these two chemical potentials. And you see, it's a little bit like doing atomic spectroscopy in optics. You have transitions. If your photon comes with the right energy, it's absorbed, and you can measure that. Here, we have an energy scale. It's a gate voltage. We can convert that gate voltage to an energy. And we can now do transport experiments that tell us exactly at which energy a particular state in the quantum dot is. So we can measure state after state, and we can do that actually with very high precision. Okay, that's the scheme of this. Now, let me show you a picture from the lab. I told you we need low temperatures. We need temperatures that are much lower than all other energy scales involved, because then we can forget about thermal excitations. So you see here on the left-hand side, a typical dilution refrigerator. So this has changed over the last 20 years dramatically. 20 years ago, a dilution refrigerator was a major piece of equipment that was very expensive. These days, they are still expensive, but the technology has changed to an extent that you can buy it privately if you have enough money, put it in your garage, plug it in, push the button, and it goes to 10 millikelvin. No other infrastructure required. That's a major step forward. So at the very bottom of this dilution refrigerator, there's a temperature of 10 millikelvin. We have very little cooling power, so have to be very careful with wiring. And then at the bottom here, this metal picture is at the bottom of the left one. You have this tail, and at the bottom of this tail, there is the sample, and the sample is connected with wires through filters and a lot of stuff all the way up there. And then at the very bottom of the system, we have a little circuit board where our sample sits, where we have connectors for high frequency and low frequency. And all of this has to be done very, very carefully in order to make sure that the samples are really as cold as you want them to be. Okay, that's how the lab looks like. Now, let me come to real life systems and start out with the two basic qubits. So the simplest you can imagine. The simplest qubit you can imagine is a single electron spin in a single quantum dot. So think of just a potential minimum that has one confined state and 1 electron in this confined state. Now you know that from Pauli's principle that this electron can have 2 spin configurations. If there are no external conditions, say no magnetic fields, no electric fields, no other symmetry breaking, then these 2 states are completely equivalent. Up and down are exactly at the same energy. And the qubit then is whether the spin is up or down. Now, in order to define up or down, you need to break the symmetry. For example, by applying a magnetic field. If you apply a magnetic field, then you have a Zeeman splitting of these states, and then the up and down have a slightly different energy. You can also break the symmetry by other means, for example, by spin-orbit interaction. So that's what we call a spin qubit, because the up and down of the spin is encoded in the quantum dot. The other very simple qubit is a charge qubit. So now you take a double quantum dot, 2 quantum dots that are tunnel coupled, and you take 1 electron in this double dot. There are 2 energy levels, but only 1 electron. And in a classical language, you could just say the electron is on the left or on the right. Now, because it's a quantum electron and there's tunneling, it can be in a superposition of both states. So that's what we call a charge qubit, and that's the simplest version of that. There are very complex qubits these days that are designed to achieve certain purposes, but I will not go into that. We will stick with the very basic qubits and see what are the pros and the cons. Okay, now for the spin qubit, there's this paper by Danielos and David DiVincenzo from 1998, where they basically said, let's assume we have 1 electron under control in a quantum dot, and then we put various quantum dots together, and that allows us to build a quantum computer. So the schematic here is on the left-hand side. You see the gate configuration. The left bars are these gates. They're very similar to what I just showed you before. So they define islands here on the left and on the right. And you see that there are spin orientations shown here. And then there is a coupling between this left and right dot by this tunnel barrier, which is tunable. Now, on the right-hand side, you see an extended version. So you see there are various of these islands. Each of the islands supposedly contains 1 electron. Each of these electrons here can have an up or a down spin. And now the idea is that you can control the coupling between the dots by opening and closing these gates. And you can control the spins by acting with 2 magnetic fields. One of them is a DC magnetic field. So this DC magnetic field, in this case, it's perpendicular to the plane. It gives rise to a Zeeman splitting. So the up and the down spins have a slightly different energy. And then there's an AC magnetic field. And this AC magnetic field is meant to flip the spin. So the idea is that, for example, if you have many of such qubits, the idea would be that you prepare a specific spin configuration in each of the quantum dots. That would be the input data of your quantum computer. And you do that by using that AC magnetic field. Now you would argue, well, the problem is this AC magnetic field acts on all the quantum dots. Now, there is an idea, and that's actually, it was a good guess at that time, more than 20 years ago. These days we can do it. The Zeeman splitting in each of these dots depends on the electronic G factor. The G factor in vacuum, as we know, is 2 with a very good precision. In a semiconductor, it's not 2. For example, in gallium arsenide, it's minus 0.44, and that's a band structure effect. And it's not only a band structure effect, it's actually something that depends on electric and magnetic fields. So you can, by having local electric fields, as indicated with these bottom electrodes here, you can locally change the G factor. And so the Zeeman splitting in each dot is a little different. And that allows you to individually address each of these dots by the corresponding microwave field that you apply. So the idea would be that you prepare your spin state in a specific configuration in each of the dots. Then you do the calculation by coupling neighboring dots. It's only next nearest coupling in this particular configuration. And the whole thing is noted here with this Hamiltonian that describes the system. So the left-hand side of the Hamiltonian is simply the Zeeman splitting, that's the G factor times the magnetic field times the spin operator. And on the right-hand side, that's the coupling, that's, if you want, the calculation process, that's the exchange interaction, and the Si and Sj are the spins in the two neighboring quantum dots. And if you sum over all of them, that basically does your calculation. So this has 1, 2, 3, 4 spin qubits have been realized, but we are far from some operation on the 10 plus qubit level at this point. Okay, now let me show you some data. This is early data from 2004. Again, you see these gate electrodes, you see this little island here. This is what I would call a charge qubit. In this case, it's the charge on or off the dot. It has only a possibility to go to the left reservoir here. And then there's a detector here that I will come to. And this detector has a conductance that depends on whether the electron is here or not. You could think of this simply being a tunnel barrier. A tunnel barrier depends very sensitively on its environment, exponentially sensitive. So if there's an electron on the left, the tunnel barrier will be more closed because of Coulomb repulsion. If it's gone, it will be more open. And on the right-hand side, you see the current as a function of time. When you see it has ups and downs, and that corresponds to the electron on the left being on and off the dot. So this is a single shot charge readout, and it allows you to tell exactly at a given point in time where the electrons are. Now, how about the spin? That's more complicated because the spin doesn't change the electric field. So what you need to do is the following. This is the single shot spin readout. It's meanwhile also called the Elsermann readout because Jeroen Elsermann was the PhD student in Delft who developed all of that. So now what you do is the following. Look at the left here. It's a quantum dot with one level and possibly one electron. Now you see there is a bias between source and drain contacts. And now you see that the state is above the chemical potential on the left. So the state is empty because it's above the level. Now you lower that state below the Fermi level in the left contact. So an electron can tunnel into that state. Now you see two states here, and they are Zeeman split. So the splitting between these two is Zeeman splitting, and it is small compared to the lowering of the energy. So an electron can tunnel into the dot, and it can go to the lower spin up state or to the higher spin down state. It's accidental. There's an equal number of spin up and spin down electrons. So one of the spin states will be populated. They differ, however, slightly in energy. So that's the loading phase. Now you go to the readout phase. So you raise the state. Again, it's a time-dependent voltage that you apply. And you do it in such a way that the lower spin down state is below the chemical potential on the left, and the higher spin up state is above the chemical potential. So now, if you had loaded the lower spin up state, it can't escape, it's stuck. If, however, the electron went into the upper spin down state, it can leave the quantum dot and it's gone. So now you see you can, what we call spin charge conversion. Now you play the same game as before. You just take the quantum dot and you measure what is its charge occupancy. If the charge occupancy was 1, then you know you had a spin up state. If the charge, then you know, yes, you have a spin up state. If the charge occupancy is 0, you know you had a spin down state because the electron left. And on the right-hand side, you see such time traces. So you see, first you load the electron in, then you try to find was there an electron left. In this case, nothing. So there was no electron left after the readout phase. However, if an electron enters the dot with a different spin, and you see here you suddenly monitor as a function of time how the electron leaves the quantum dot. So this is how you can read out what the spin of the electron in this quantum dot was. Okay, now this is fancy. This is Rabi oscillations. So what you see is basically a coherent oscillation that is driven with an RF signal. So you can think of this, that these are spin rotations now. Let's have a look at this. This is a double quantum dot. On the right dot, there's a spin-up electron. There's another electron coming in. And you see, this is also, in this case, spin-up. So you have two spin-up electrons. And you know, two spin-up electrons, if they are in the same state, they have to form a triplet. So first, this spin-up electrons goes into the left dot because there's no electron yet. Now it wants to move to the other side, but it cannot because the electron on the right has also a spin-up, and it costs too much energy to go into that triplet state. So you flip this electron, you flip the spin by applying an RF signal, flip the spin down, and now it can move over and then form a singlet state with the electron on the right. And now, depending on how you flip it, if you just flip it by pi over 2, it can go. If you flip it by pi, it cannot. 3 pi over 2, it can again. And so it depends how long your RF signal acts on the quantum dot, whether there is actually a current or no current. And on the right-hand side, you see this current as a function of time for different powers here. So the burst time here shows you that there are periodic oscillations. That's this rotation of the spin. And you see that the more power you use, the shorter the oscillation in time, because you rotate faster. So, and that's a very nice thing, that you can actually measure coherent spin oscillations in a solid, in spite of the fact that you have all these nuisance around: phonons, photons, fluctuating electromagnetic fields, nuclear spin, spin-orbit interaction, and so forth. So that's a phenomenal success, I would say, in condensed matter physics. 30 years ago, people would have thought that solids are so dirty that it will never be possible to see coherent quantum effects. But now this has been shown in a number of different systems, and this is one of them for spins in quantum dots. So here's a table that I copied from a recent paper from Christoph Klöffel and Daniel Loss, where they looked at a large number of different quantum dots. I just showed you one here, lateral quantum dots in gallium arsenide, but there's a whole zoo of these quantum dots around. And there are different lifetimes, spin lifetimes, charge lifetimes. I know this table is way too small for you to read it probably, and it should just give you an overview what is possible. Also, the materials are interesting here. So gallium arsenide is the best material in the sense of how you can control the system and how noise plays a role and things like that. Silicon is a fantastic system because industry uses silicon, and I will come back to that. Now, many people work on indium arsenide, silicon, germanium, electrons and holes, carbon nanotubes, graphene, and the list goes on. And I think the best qubits today are in silicon, but the others have other advantages that should not be neglected. So let me just try to summarize materials. I think everybody, each of you, works with a material, I guess, and there are certain parameters that are important. And I listed here on the vertical axis some materials. It's not exhaustive here. N-type gallium arsenide, this is the one that I described to you mostly so far. Indium arsenide, indium antimonide, these are narrow gap semiconductors. Then there's a very fancy one, which has what we call a broken gap, where electrons and holes coexist. Indium arsenide, gallium antimonide. There's graphene and silicon. So one important parameter is the so-called RS parameter. The RS parameter tells you how important are electron-electron interactions. And what you see here is it's E squared over L. It's very simple. It's the Coulomb law. It's the energy, the Coulomb energy. It's the charge squared divided by the distance between two charges. Now, what is the distance between two charges? That is typically given by the carrier density. If you know the carrier density, you can calculate the average distance between two charges. And it turns out that for most of these systems, this L is very similar, because it depends on the doping densities that you can achieve and so forth. So And because the L actually goes with the square root of the density, all of this is within 10 nanometers or something like that. Now, the kinetic energy is another story. The kinetic energy of the particles in a solid is basically the Fermi energy, at least in a doped semiconductor, or where you induce carriers with a gate like in graphene. So it's the Fermi energy. And the Fermi energy also depends on the density, obviously, but it has a very important parameter in it, which is the effective mass, which comes from the band structure. So one typically says if Rs is much larger than 1, then the system is completely dominated by interactions. If it's less than 1, then you can do as if the carriers don't see each other. You can treat them as individual particles. And for n-type gallium arsenide, we are in a situation that you can almost forget about interactions. You can just think about your energy levels, fill them with spins, Pauli principle, and so forth. Very simple. For example, if you go to holes in gallium arsenide, because they are heavier, the holes, it's the opposite. Interactions are everything. So the single particle levels that you calculate, they are not very accurate. It's all dominated by interactions. And now for narrow gap materials, once the gap gets small, also the effective mass gets small, and so interactions are even less important. For graphene, it's funny. That's because of the dispersion relation of graphene. It turns out that they're actually fixed. For linear dispersion, you can show that all of this is independent of carrier density and comparable to gallium arsenide. It's also interesting. And for silicon, it's also depends whether you have electrons or holes. For holes, interactions are very important. For electrons, they're intermediate. Now you can ask yourself, how does the spin couple to the environment? And this is what we call spin-orbit interaction. There is an atomic component of spin-orbit interaction. We all know it's a relativistic effect. It basically means that an electron on an orbit, on a circulating orbit, creates a magnetic field. It's like a current that goes in a circle. That creates a magnetic field, and that magnetic field couples to the spin. And in a solid, it's again something that comes out of the band structure. And some of it can be tuned by electric fields. This is what we call the Rashba contribution. And in gallium arsenide, spin-orbit interactions are weak. We have to work hard to actually see them. In indium arsenide and indium antimonide, they are strong. They are obvious. For graphene, they are predicted to be weak, and the first experiments are coming up now. But it's not very well established yet. For silicon, they are super weak. And as a rule of thumb, you can go, if you think about the periodic table, you can say, the further I go down in the periodic table, the stronger spin-orbit interaction. Heavier atoms have stronger spin-orbit interaction. So silicon is fairly high up in the periodic table, and carbon is element number 6 in the periodic table. So anything having to do with spin is very weakly coupled in graphene and in silicon. Now, right column, hyperfine coupling. That is the coupling between nuclear spins and electron spins. So nuclear spins are all over the place, right? Any solid has nuclear spins. Now, the question is, how strong are these nuclear spins and how many are there? So qualitatively, it depends on the isotope. So most isotopes have nuclear spins. There are very few that have none. I will come to that. So for gallium arsenide, all isotopes have lots of nuclear spins. So, and strong nuclear spins. So hyperfine coupling is strong. It's actually true for all 3,5 semiconductors. Now for graphene, and it's not just graphene, it's true for carbon nanotubes and all carbon-based materials, they consist to 99% of carbon-12. And carbon-12 has no nuclear spin. So all carbon-based materials by construction have very few nuclear spins, much weaker, orders of magnitude weaker than typical other materials. Silicon is different. Silicon has different isotopes, but isotope number 28 also has no nuclear spin. And these days it is possible to make silicon entirely out of the isotope silicon 28. So if you can do that, then you also have a basically nuclear spin-free material, and you get rid of hyperfine coupling. You can imagine if you look at an electron spin, and there are lots of nuclear spins around, they will affect this electron spin by magnetic dipole interaction, and that will lead to decoherence. The electron spin will start flipping. But if you can get rid of the nuclear spins, as you can in carbon-based materials and in silicon-based materials, then this is a big step forward. Okay, now I think it's time for a short break, and we can start the break with a question. So, Bodzena, can I ask you to maybe flash that question? You might have to unshare me. And so let's take a 5-minute break and you can answer this question.
I wanted to open the poll and it's not working for me again. It's frustrating.
Let's see, I can't use my cursor anymore. It's gone.
Okay, it should work now.
Yeah, I think it's on my side, but I lost completely my cursor. So
No, I opened the poll now.
and it's coming.
Yes, it's coming. I'm just waiting for everyone.
Good.
Okay, I see that.
Can you see my cursor?
Yes, 34 people have answered out of here, so yes, someone is answering, so I'll give it another. How long do you want me to give it, Klaus?
Yeah, I think it's fine.
It's fine? Okay, so I'll close it and I'll share it with attendees. I think, is it visible?
Yes, I see it now. Wonderful.
Okay. I figured it.
We have lots of people in graphene and in nanowires and others which I missed. Okay. Good. Thank you. So I think we can move on.
Yes.
So I have to share again, huh? Do you see my screen again?
Yes.
Okay. So welcome back. So let me show you here some nice figure that I copied from Tadeusz Ladd from one of his papers. This is about possible ways of implementing spin qubits in silicon. And there is one possibility here, which is using a donor. So you take a perfect piece of silicon, but you place one phosphorus atom at a specific location that needs atomic precision STM. And you have one electron, one free electron. And that gives you a very controlled system because it's basically as clean as an atom. And the group of Michelle Simmons in Sydney is the pioneer in that and has really demonstrated a lot of interest in qubit physics. Another approach is using standard MOS technology as it is used in semiconductor industry. As I said, if you get something working with silicon MOSFETs, you're in business because we know how to upscale that. And many people are trying that. The problem is that MOS transistors, they have a silicon and an oxide, and you induce the carriers with a gate. So the potential is pretty disordered. So you have to make very small transistors, which is not impossible. And Intel is trying to do that. So that's a route that tries to make your system smaller than the length scales of the imperfections. And that is a potential to go. And then there's a new direction using silicon germanium, which would be compatible with silicon. There are groups in Delft and also in Austria that are working on that. And then everything is done epitaxially, like in gallium arsenide, low disorder, but there are also challenges, as you see here on the right-hand side. Okay, so here a few times, decoherence times of spin qubits. So you see the numbers here, there are T2s and T2 stars and all kinds of indices. So the real number, if you want, is the T2. That's the one that counts. So T2, usually one measures ensembles. Either one measures many spins or one measures the same experiment many times in a row to get enough signal to noise. So that's what's called the T2 star. The T2 star is the coherence time after many averages. And the T2 is really if you measure it for one individual particle. And then there are various pulsing schemes, how you can improve that, and echoes and so forth. I don't want to go into that. But just look at the lowest number, phosphor donors and 28 silicon. So silicon 28, as I told you, has no nuclear spins anymore. You place one phosphorus atom at a specific location. This phosphorus atom has no colleagues around with nuclear spins. It lives in a vacuum of nuclear spins. And the coherence times are comparable to what you find in ion traps, where in ion traps, you do not have neighbors because you are in perfect vacuum, right? So the weak coupling in ion traps can be realized for the phosphorus donors in 28 silicon. Of course, the problem with these donors is how do you address them? How do you put in the quantum state? How do you read it out? But the coherence times are really amazing. Okay, now let me move on. Let me show you a little bit the physics that you can do with qubits. One thing is that you try to build better qubits or to build a quantum computer or something like that. And the other thing is to do physics with it. And that has two reasons. One of them is the systems have become so perfect, the technology is so nice that you can do physics that you couldn't do before. So physics enables technology, but technology also enables new physics. And that's nice. And the other thing is, of course, the more we understand about these qubits, the better for building a quantum processor. Okay, let me start out with a very simple picture. Let's look at a scale, as you see on the left-hand side, and this scale is completely in equilibrium. And usually what we do in our experiments is we measure in equilibrium. So if you take a resistor, apply a voltage, measure a current, you usually get a linear curve. We call this Ohm's law. And this is something that holds in equilibrium or quasi-equilibrium. If you apply large enough voltages to a system, this line will not be linear anymore. Ohm's law holds what we call the linear response regime, where we are basically describe the response to the external voltage with the properties of the system in equilibrium. Now, we all know that if you look in great detail, there are fluctuations. There are classical fluctuations, there are quantum fluctuations. So if you measure a current with very high accuracy as a function of time, then there are fluctuations. And we need to understand these fluctuations, or we could even use them. So assume now that you have a current of 1 microamp that flows through your circuit. Maybe you're doing an experiment. Then you ask yourself, how many electrons per second does this correspond to? So we don't have to go to the Pauli. You can do it for yourself. Just make a rough estimate. 1 microamp of current, which is sort of a typical operational current. How many electrons per second? And well, it's not very difficult because we know that the charge is 1.6 times 10 to the minus 19 amp seconds. So that roughly corresponds to 10 to the 13 electrons per second. So you see where I'm going? I start from fluctuations, and now I want to see whether the fact that the current is composed of individual electrons, whether that situation actually leads to fluctuations. And here I would say that leads to fluctuations that are on the scale of 10 terahertz. So 10 to the 13 per second. If you can measure that fast, you should be able to see that individual electrons come into your system. That's hard. So what we try to do is we try to go to lower currents to reach, for example, the regime of 10 electrons per second. That's 12 orders of magnitude in current. So that would correspond to something like 10 to the minus 18 amps or attoamps. These are currents that no electronic amplifier can measure. So let me go back to our simple picture of the capacitor. So you take 2 capacitor plates, you calculate this energy it takes to charge the capacitors. We have done that before, Q squared over 2C. And as I told you, when you take 1 nanofarad, 1 electron charge, you find a super small energy scale. Now, when you make these capacitor plates 1 micron by 1 micron, by some means, then you can increase that energy scale because it's proportional to 1 of the capacitance. And this one you have seen before too. This is situation of Coulomb blockade, and this is single electron transport. And this is something you can tune with your system with the gate voltage that you have seen. Now, in this system, we are guaranteed that the electrons go 1 by 1. What we now need to tune are the tunneling barriers left and right, because they control the rate with which the electrons come. So let me do probably the simplest experiment that can be done in condensed matter physics. So let's look at this picture on the left-hand side. You see all of those gate electrodes. You see the black is the surface of gallium arsenide. And the electron gas is depleted below those grayish areas. In addition, we close off to the right. And so this electron resides in this island, and it can only go to the reservoir in and out. That's the only possibility for the electron. Then you see there is another gap here, and there can be a current flow here on the left-hand side. And this current flow is used, as before, to measure whether that state is occupied or not. So now let's take an energy diagram. Let's assume there is a Fermi sea in the reservoir. And so there's a distribution, a Fermi distribution, and that is broadened by kT or 4 kT. In the quantum dot itself, there's a discrete state. And the question now is this discrete state close to the Fermi energy? Is it above it or is it below it? It's clear if the state is up here, it's empty. If it's down here, it's full. If it's somewhere in this regime where the Fermi distribution is smeared, it is somewhere in between. And that's something we can measure. So if we measure this current here through this, what we call a detector as a function of time, you see it switches between 2 levels. And these 2 levels correspond to the electron going in and out of the dot. Look at the time scale here, about a second. So we have events on the time scale of few per second, 10 per second or so. So in terms of current, let me remind you that's attoamps, 10 to the minus 18 amps. The smallest current you can measure with conventional electronics, and I should say not commercial electronics, but the best home-built electronics, is around femtoamps. I would say more like 10 femtoamps. It depends, of course, on your averaging time and stability of your system, but it's more than 3 orders of magnitude away from what you see here by just counting electrons. Now you see there's a lot of information in such a trace. One thing is how steep is it? The other thing is how many events are there per second? And then there is what's the average time in the out state and what's the average time in the in state? And this average time you can directly convert to a tunnel rate. It can happen that the electron goes in and goes out again, goes in and goes out again. Of course, you have as many in and out events, as many in events as you have out events, but the average time in the in and the out state can be very different and depends on where the state is relative to the Fermi energy. So now we measure these in and out times as a function of this state in the quantum dot that we move up and down relative to the Fermi energy. 0 means Fermi energy. So when this state is at the Fermi energy, then it's resonant, and otherwise it's above or below. So let's first go to energies way below the Fermi energy. Well, it's clear that the out, I can't get out, the electron can't get out. Once it's out, it rarely goes out, then it's in very quickly. So the tunneling in rate is very high. On the other hand, if the state is far above the Fermi energy, then I'm rarely in that state, it's rarely occupied. But once it's occupied, the out rate is very fast. Now, look at what happens directly at the Fermi energy. The two rates are not the same. It's interesting. So you have a state, a discrete state in a quantum dot. You have a Fermi energy on your source contact, and the rate to go into the quantum dot and out of the quantum dot is different. And it's actually different by a factor of 2. And the rates can be made the same at finite energy here. So let's have a look at that. What's happening? Well, we have a thermal broadening in our system, which in our case, 50 millikelvin is kT, and about 4 kT is this thermal broadening. So now we can write down the rates to go in, and the rate to go in is the tunnel rate to go in times the occupation of the reservoir. That's given by the Fermi distribution function. Now to tunnel out is the tunneling out rate, and of course then you need the probability to find empty states in your reservoir. That's 1 minus the Fermi distribution function. And remember that the gamma in and the gamma out, we can directly determine here. We have them in a measurement protocol. So one thing is we fit these functions, and the fit functions are nothing else than the Fermi functions, or 1 minus the Fermi functions. Or in other words, the only free parameter we have is the temperature, which is 50 millikelvin. Okay, now what is the W in and the W out? That's also interesting. Look at the extreme case once we are well below the Fermi energy or well above the Fermi energy. The limiting cases are again different by a factor of 2. So what we conclude from that this reflects the degeneracy of the state. Let me explain to you what I mean by that. So let's assume the electron sits in the reservoir, or many electrons sit in the reservoir, and there's a discrete state in the quantum dot. Actually, there are 2 states at the same energy because of the Pauli principle, right? There are 2 spin degenerate states. So this one electron that tries to go into the quantum dot has 2 places to go. So the probability to go into the quantum dot is the tunneling barrier height, so the tunneling rate, and the number of states you go into. So you have 2 states to go into. Now, let's assume the electron is now in one of those states and wants to go out. Well, it comes from one of those states. So there's only one possible path to go out. There are 2 paths to go in, and there's 1 path to go out. And that directly reflects the degeneracy of the state. Now, it's super trivial. We all knew that, right? We all knew that every state is twofold degenerate because of spin degeneracy. However, if you want to measure the degeneracy of a state, it's actually not that trivial. And there are a few methods in optics where you can do it, but I'm not aware of any method in transport. So just by doing a resistance measurement, you get the degeneracy of a state. Now, there's something else which is interesting. That's this energy, the energy between 0, where the Fermi energy is, and the energy where the two rates are the same. The tunneling in and the tunneling out are the same. And you see, you can directly go into this rate equation model that I showed you before. It contains everything. You just make the W in and W out the same. You calculate where this happens, and you find that this is simply given by KT times logarithm 2. And I guess that this rings a bell for many of you, because that is the minimal energy for a classical qubit to be erased. Erasing a qubit means that there is no information stored in that qubit. And that's exactly, let's say our qubit is the electron on the dot or off the dot? That would be the information in the qubit. Well, if the W in and the W out is exactly the same, or the gamma in and the gamma out, that's exactly when you have erased that information. So that's why this energy that you have to pay for that is KT times logarithm 2. So now you can actually do the explanation of this experiment also in terms of classical information science. So that's a twofold degenerate state. Now let's go to the second electron. I don't show you the raw data anymore, just the analysis. So this left-hand figure you have seen, one electron. Now the second electron. And you see here, the green is twice as high as the blue. Now it has reversed. The green is half as high as the blue. So let's go back. What did we learn for the first electron? For the first electron, one option to go out, two options to go in. Actually, this arrow, here we are. Two options to go in, one option to go out. Now, if you have one electron already on the dot and you want to bring in the second one, there's only one state because one is already occupied. However, if you want to go out, then either of the two can go out. So the probability has completely reversed. Now it's easier to get out than to get in. The tunnel barrier remains the same. So the tunnel barrier for one electron or two electrons or in or out is the same. But the number of landing spots, if you want the density of states that is available where you can land, has changed. So you see the degeneracy again plays an important role here. Now you can, of course, do 3 electrons. It's the same as 1 electron. 4 electrons, same as 2. We can go to 5, 6, 7, 8. And you see this going back and forth between the different rates to go into the dot and off the dot. Now, I should mention here that this dot was tuned to work as perfectly as the data shows here. Usually it doesn't work that well. And the reason is, you see, I have completely neglected interactions. And I gave you the argument before, because in gallium arsenide, there's a reason for that. Because the kinetic energy is so high, because the effective mass is so low. So the kinetic energy is much higher than the Coulomb energy. However, it's not negligible. And in most cases, what happens is you fill in the first electron up and the next down. That's the normal thing. Then comes the third one, which is up. And then the fourth one has the chance to either be parallel or anti-parallel. And anti-parallel is easier than parallel because then you have to pay exchange in direction. And now it depends on how much energy you win or lose, whether you go through this odd even sequence or not. And you know, in the periodic table, this odd even sequence is broken quite early. The S shell is up, down, but then already the P shell, 3 spins are in a row, and that's because of exchange in direction. And the same thing can happen here. So that's a beautiful example which was fine-tuned. In real life, you will not have this odd even sequence for many electrons. And let me just add here, gallium arsenide is a very simple semiconductor. If you take silicon or graphene, you have an additional degree of freedom, which is the valley degeneracy. And this valley degeneracy, everybody knows it, it has been calculated and so forth. There is no experiment yet that shows that the ground state of one electron in a carbon-based material has a 4-fold degeneracy. It's something that we are trying right now, and it's not so easy. But you see that these fundamental experiments can be done, and they can be done because we have this advance in qubit technology. Okay, now let's go back to 1 electron in a double dot. So the previous experiment was the simplest one you can think of. 1 electron, 1 dot, 1 lead. Now we have 2 dots, but we switch off the leads. No contact anymore to the chemical potential of the lead. So the electron has only two opportunities. It can be on the left or on the right. It can't leave. Well, the experiment that we can do is the same as before. We have our detector on the left, and the detector sees whether the electron is on the left or right because it has a different interaction, a different distance, and the capacitance is different. And therefore, again, this current fluctuates between two numbers. And the two numbers tell us whether we are in the 0-1 state or 1-0. 1-0 means one electron on the left, 0 on the right, or the opposite. And these two states, if properly tuned, are degenerate. Okay, now let's do the same experiment as before. We basically measure the tunnel rate, right? Remember, we can measure how much up times we have in the current, how much down times we have. We can convert these times to a rate. And so we can plot this rate from left to right and from right to left. We know a downturn in current is a right to left, an upturn in current is the opposite. And we do that as a function of the distance between these two levels. So at 0 detuning, as we call it, the two levels in the two dots are in resonance. And then we either move them this way or we move them that way. And because the system is completely degenerate, you see that the rate is maximum when the levels are aligned, and then it decays as you misalign them. And it's completely symmetric with respect to left and right. Same rate. No surprise. Now let's add one electron. Let's have 2 electrons in a double dot. No connection to source and drain. 2 electrons in a dot. So how does it look like? We can either have the 2 electrons distributed, that's what we call a 1-1 state, 1 electron on the left, 1 electron on the right, or we can have both electrons in the same dot. That's what can happen, right? So from the outside, we have again our detector here. Our detector just monitors this 1 electron that goes back and forth. The other electron that is stuck doesn't make a difference. Now, I'm using words like this and that electron, and we know this is not correct language in quantum mechanics. Electrons are indistinguishable particles, but in this kind of measurement, really what we see is whether a single charge moves back and forth and when it does so. So let's do the experiment. And something funny happens. You know, I measure this current here, and indeed, this current goes up and down. That means an electron goes back and forth. But every now and then, there are times when nothing happens. It seems that the system is stuck. And then there are times in between where it goes back and forth. So there are now more timescales involved. There's obviously a timescale to go in from left to right, or to go from right to left. And there's a third timescale. So what's happening here? Well, now you see that in a very simple way, the spin comes in. Because what I've not considered so far was the spin. For a single electron, it's irrelevant. Now we have 2 electrons. And now we have to ask ourselves whether the spins are aligned or not aligned. So you see, if the 2 electrons are in separate dots, they don't care about their spin orientation because their wave functions basically don't couple. Anything related to exchange interaction is related to wave function overlap, which is basically 0. So these 2 electrons can have any spin orientation with respect to each other. They can be in a singlet state or in one of the triplet states. They don't care. However, if the 2 electrons are in the same dot, their wave functions strongly overlap. So suddenly exchange is very important. And exchange means that the singlet state is much lower in energy than the 3 triplet states. Right? It's like in the hydrogen atom. If you have a molecule, I should say. In the hydrogen molecule, the 2 electrons form a singlet state. The triplet state is far away in energy. Same is true for the helium atom, 2 electrons in the singlet state. So if the 2 electrons are in the same dot, they need to have a singlet spin configuration. If they are in 2 dots, whatever. So now what happens is the following. You see that there are regions with spin blockade. What that means is the following. If the 2 electrons have the same spin, then the right electron cannot tunnel to the left dot because the triplet state is too high in energy. It can't get there. So nothing happens. Nothing happens until by some mechanism the spin of the right electron is flipped, and then it can join the electrons on the left. And then once that is the case, we see a pattern as we know it. Electrons going back and forth, and the rate is determined by the tunneling barrier. Okay, so now what I show you here is the rate from 1, 1 to 2, 0, and from 2, 0 to 1, 1. So blue is one direction, red is another direction. And now you see they are not the same anymore, right? For one electron, they're exactly the same. Left, right, right, left is the same. Here, it's not the same. And why is it not the same? Well, the reason is, again, a very simple one. If you have a 1, 1 state, there is just 1, 1 state. However, for the 1, 1 state, it has 1 singlet and 3 triplets. So that's 4 states, and they are all degenerate as long as the exchange interaction is negligible. So for the 1, 1 state, the electrons are in different quantum dots. They don't see each other, no wave function overlap, no exchange. So singlet and triplets are degenerate. These are 4 states. Now, the 2, 0 state, on the other hand, as I told you, now the electrons are on the same dot. There is only 1 singlet state that they can take. The triplet states are up in energy. They become irrelevant. So in one direction, you have to go to a singlet state. In the other direction, there are 4 states you can go to, 1 singlet and 3 triplets. And that is exactly the factor of 4 between the blue and the red trace. So you can directly measure, again, the degeneracy of a many electron state, of a 2 electron state. And the degeneracy here is determined by the spin configuration. So you see, no complicated experiment, very simple experiment, only 2 electrons. We are monitoring this, look back at the time scale, seconds, slow experiment. And nevertheless, the system is stable enough to tell us about spin configurations. Okay, now we understand why forward and backward tunneling is different for this system. So, and you can do some calculation here, and there's a related experiment that I should refer to where people did similar things with optics, and it all makes sense. Now, what flips the spin? Okay, there is a time scale for the spin flip, and it's seconds. We can actually tune it. What flips the spin? Well, there are spin conserving tunneling events, and there are spin flip tunneling events in this system. So one thing is you go back and forth, and as you go back and forth, this is a motion in real space. It's an orbital motion. If there's spin-orbit coupling, orbital motion means you flip your spin while you move. Also, so that happens while you move. Or you can couple to nuclear spins. I told you gallium arsenide has strong hyperfine coupling. So suddenly the spin flips. You just wait, and suddenly it flips because it couples to nuclear spins, and then it can suddenly go. So we can distinguish between spin-conserving tunneling and spin-flip tunneling, depending on which states we're looking at. And this means that we can actually understand what's going on. So let's look at this configuration. 2 electrons, 1 left, 1 right, both spin down. So the red electron, again, I apologize for talking about different electrons because they're indistinguishable particles, but for the sake of understanding, I still do it. So the red electron wants to go to the right, but it can't because it has the same spin. And then it would have to form a triplet with the right electron, and the triplet is up in energy. So the right electron can flip its spin, and then the 2 can get together on the right-hand side. So that requires that suddenly the right electron flips its spin. That's hyperfine interaction. And that's coupling to nuclear spin. That's spin rotation inside a dot. And if we apply a finite magnetic field, we can actually flip that part off, because the nuclear spins have a Zeeman splitting which is much smaller than the Zeeman splitting of the electrons. It's because the nuclei are 2,000 times heavier than the electrons. So at zero magnetic fields, these spins can talk to each other. As soon as you apply a finite magnetic field, the Zeeman splittings are so different that spin flip spin flips by exchange is not possible anymore because of energy. So this is something that happens, but we can switch it off. Now, what about the following? We start in the same configuration, both electrons spin down. Now, if you have a tunneling process that allows you to flip the spin, and that is what we call spin-orbit interaction, then this transition can take place. So now by measuring these type scales, you can actually learn something about the spin-orbit magnetic field and about the spin-orbit scattering rate. And what you find is that obviously not every tunneling event flips the spin, but a few of them will. So we can measure spin conserving and spin flip tunneling events and compare them. And that's what you see here. So on the left-hand side, you see this figure. So you see here spin conserving tunneling and spin flip rate. You see here they go together. They are proportional to each other. But you see the axes are quite different. And the dashed line shows you that 4% of all tunneling events lead to a spin flip. So if there were no spin-orbit interaction in the system, like in silicon or graphene, there would be no spin flip tunneling. But because there is finite spin-orbit interaction, you move an electron from the left to the right dot. That means moving it by around 100 nanometers. So you know the strength of the spin-orbit interaction, so you can calculate what the probability is to flip the spin. And actually, the ratio between these two tunneling rates, spin conserving and spin flip rate, is simply given by the distance between the two dots, divided by the parameter that governs the strength of the spin-orbit interaction. And what we find is, we know the distance between the dots. So the spin-orbit length is around a micron, and that is compatible with what other people have seen. So you see, by doing really very basic physics, we are just looking at what one electron does as a function of time. And we get very basic information on processes in the semiconductor that lead to spin flips. And spin flips are, of course, detrimental for any spin qubit that you might want to have. Okay, I think I prepared, of course, much more, but that's way too much. And I want to stop here to also have time for some questions. So the last part that I showed you, it was all done by PhD student Andrea Hoffmann and postdoc Willem Meisy and my colleague Thomas Ihn. And I show you here one exemplary curve, how you see that one can monitor the behavior of electrons as a function of time. And I showed you how we can measure spin degeneracies, we can measure spin blockade, and we can actually go a step beyond that, and we can learn something about electrons out of equilibrium, not just by watching what they do if you leave them alone, but by actually drive them out of equilibrium and monitor their behavior then. And that's interesting because that's how a quantum computer works. You drive it out of equilibrium, and then you want to understand how the processes in that system work. So electrons out of equilibrium, that's, I think, a topic that will govern us for many years to come. So let me conclude here. I thank everybody who has still been patient enough to listen to me. And I would be super happy if you would ask questions. Is there anybody who wants to ask?
Okay, Klaus, thank you very much for that excellent talk. And I have a question that's quite, well, I would say related to the topic, isn't it? There are basically several concepts of qubit, and one of them is related on the position of the electron in the quantum dot molecule or double quantum dot left or right. And for me, it was always a bit puzzling, because while spin up and down are clear quantum states, and when we perform the measurements, there's clear outcome. For this left and right, is actually a continuum of possible outcomes of the measurements, and also there are overlaps. If you keep the electron in the left quantum dot, there's always a chance you will measure it in the right and vice versa. So how this concept actually work?
Yes, that's a very good question. Thank you very much. So I think there are various aspects to your question. One of them is, of course, in an experiment, you always measure a variety of outcomes, also for the spin up, spin down. Because I showed you in one of the early slides this, what people call spin to charge conversion. So at the end, you determine what the spin was by measuring where the electron is. And because any experiment has noise and finite resolution, you will measure not a clear-cut yes or no answer, but you will get distributions of spin up and spin down, or distributions of electron left and right. So I think that's no matter which quantum system you look at, because of experimental resolution issues and also more fundamental issues, there's always a distribution. But the other question that you address is, of course, spin is a quantum property to begin with. So nobody is surprised that a spin could be a qubit. Now, electron left or right is a very classical concept. How could that be a qubit? And of course, it takes more than what I just said for a qubit. Basically, take a single well. A single well has discrete energy levels. Now you take a double well, and then you know that all the states will split, right? There is always an even and an odd state that arises from the superposition of the states at the same energy.
Yes.
And these two states, in some sense, are the states we are looking at when we talk about electron left or right, or superposition of these states.
Okay, thank you.
And let me also add something that I probably didn't say clearly enough. The charge qubits are the most simple ones. They're also simple to measure. But the charge qubits will never make it into a quantum computer because, I mean, one should never say never, because we already had many surprises, but charges coupled to electromagnetic fields, in particular to electric fields. And for example, if you have phonons in your system and there's some piezoelectricity in your material, then any 0-point fluctuation of your phonon will lead to fluctuating electromagnetic fields, and that will couple to the electronic charge. Also, any voltage source that you have has a finite accuracy and fluctuations and will couple to the charge. So charges are just super sensitive and coupled to everything. And therefore, the best coherence times that we have seen are 10 nanoseconds. I mean, compare that to seconds for spins. There's 8-9 orders of magnitude. So charges are super easy to manipulate and to measure, but they are not very coherent. I think there's still some opportunities there, but we don't know yet. Spins, on the other hand, are super coherent because you can make the environment so clean that they basically don't see it anymore. That comes with a disadvantage that they're hard to manipulate. So you have to play tricks there. And in the end, all the spin manipulation goes via coupling to the charge for all designs that I know. So the charge always comes through the back door for manipulation and for readout, but the real quantum information is encoded in the spin.
Okay, thank you.
Thank you.
Okay, thanks for interesting lecture. I would have one question. Except of graphene and older classical two-dimensional electron gases, are there any other 2D materials who would be also suitable for qubits?
Thank you, Mira. I mean, there are all these transition metal dichalcogenides. Are these the ones you're thinking of? Or the ferromagnetic ones, or?
The ferromagnetic ones.
Yeah. I think for a qubit, you need a very clean system. All the TMDCs and the magnetic materials that are around are orders of magnitude too dirty. And what I mean by that is you cannot even build a quantum dot that contains one electron, because the potential modulation, the natural potential modulation in these systems is so rough that if you put in electrons, they get trapped in random minima in that system. So assume you make, by lithography or by etching or whatever, a quantum dot potential. Then this quantum dot potential on the bottom will be so rough, it will not be a smooth potential, that when you fill in an electron, it lands in one of the random minima of this potential. And I think that is hard to overcome. I mean, these materials are getting better every day, but I still think they are, if you just talk about mobility, carrier mobility, they are like a factor of 1,000 worse than graphene. It's not a small factor, it's a huge factor. One could argue that if you could make your quantum dot potential much smaller, then you could live with the fact that there's some randomness at the bottom. And actually, that's also a little bit used by the silicon people who benefit from the enormous resolution that they have in industry. So I would not exclude it, but it's not obvious how this would work at this point.
Thank you.
Well, maybe a question related to the previous one. Well, it is true that TMDCs are dirty, which applies to the charge, but does it apply also for spin? Because we have plenty of natural defects that can bind just a single electron, and if you manipulate just the spin and disregard the charge, then it might be still quite a coherent system, isn't it true?
Yeah, I mean, the TMDCs have interesting spin properties. You know that I had this table where I characterize spin orbit as weak or strong for certain materials. If you include the TMDs, they are super strong. They are so strong that there's spin valley coupling. So the spin is not even a free degree of freedom anymore. So that's a completely different ballgame. And it's possible that one could come up with an interesting qubit idea there. Again, I would think this is maybe good for optical experiments, but not for transport because of the reason of inhomogeneities that I mentioned. But for optics, there could be some very interesting work there.
Okay, thanks.
Other questions?
Yes.
Oh, let me have the
sorry, yeah, okay, go on, Vlastik. Yeah, I was muted.
I see. Well, okay.
Go on.
Good. Thank you. Well, then my final question would be, what's the system you would bet that it make it finally to the industry? For me, it seems that quantum dots are best so far, but with problematic scalability. So what's your opinion on that?
So I would argue that the final quantum computer that we have in 10, 20 years will be a hybrid machine. I would go back to the early days of the classical computer, where we, for example, had a magnetic hard disk and a semiconductor processor, and the technologies had to work together. So I could very well imagine that spin qubits, because they are small and fast, could be used for quantum information processing, and ion traps could be used for storage because of these enormous coherence times. Now, of course, to get the quantum information coherently from a spin qubit to an ion trap, that's a challenge, and people are working on that. But I would not discard any technology yet. I think all of them could play a role in the end.
Okay, thank you very much.
Thank you.
Yeah, maybe, yeah. Thank you very much for a nice lecture, interesting one. In the first part of your talk, you mentioned that you use radio frequency signal for flipping of electrons and between two levels given by Zeeman splitting. But maybe I didn't understand well, but you mentioned that you can flip it either by, let's say, completely 180 degrees, let's say, from down up. But you also mentioned that you can flip it, I don't know, by 90 degrees. But is it possible such a transition? I don't think so. Or how is it like?
I think it is possible because it goes into a superposition state. So with these pulses, you can put it on any point in the Bloch sphere. And so if you just give it a short, I'm trying to choose.
Yeah.
So let's assume it points in this direction now. As you apply RF, it starts moving, and the longer you have it, the more it moves around on the Bloch sphere. So obviously that is an ensemble picture that I'm now
Yeah,
doing here.
okay.
So it's not the same spin that they're looking at all the time. It's always a new experiment, and it's averaged. I agree with you that if you have one spin and you apply one voltage, one RF pulse, it goes in some direction, which has some randomness into it because it's quantum mechanics. But if you do it often enough and you average, you end up on average at the same spot.
Okay.
And the longer you do it, the more you rotate.
Yeah, okay. And just a question, what about that quantum entanglement? Because there are the papers on that they manage in quantum dots this effect to demonstrate. What about your experiments? Have you tried it or somehow?
Well, entanglement, I think, is an interesting question. So if you write down the wave function of a singlet state, which is 1/2 spin up, spin down, minus spin down, spin up. Everybody learns that in quantum mechanics 1. This wave function is entangled because you cannot write it down in a factorized way. So my answer could be, of course we do see entanglement because we see singlet states and a singlet state is entangled. But of course, that's a little unsatisfactory as an experimentalist. And then probably your question comes in, can you prove experimentally that it is an entangled state? And to the best of my knowledge, this has not been done with quantum dots. This has been done with cold atoms. It has been done with superconducting qubits, that one can play with the entanglement and switch on and off the entanglement. This is yet to come for quantum dots. So that would be, I think, the real challenging part. Yeah.
Okay, thank you.
Thank you. Okay, Potzena, are we done?
Okay, if there are no any other questions, then I will once again thank you for a brilliant lecture. And we will be starting here tomorrow at the same time, 10:30. So looking forward to see you all again for the second half.
Okay. Thank you very much for
Thank you.
listening. Have a good time.
Thank
Bye-bye.
you.
Thanks everyone for participation.
Thank you.
Bye.
Bye. Thank you.